Hello, everyone. Today we have another student chapter seminar. I hope you already joined our channel Discord, and you also follow the recent work, the recent presentation and the future on our YouTube channel. If not, please follow the USACM student chapter Discord channel and also YouTube. And we wish everyone reach out to us to showcase and present their interesting work to us and to everyone who are interested in computational mechanics. So please reach out to the student chapter by this email here, studentchapter@usacm.org, and give us a title for the presentation, abstract of the work, and also a short bio of yourself. And today is our great pleasure to introduce Wahid Talk, a PhD student from Purdue University. And he's going to present his work on generative hyperelasticity with physics-informed probabilistic diffusion fields.
Thank you for the introduction, guys, and thank you for inviting me. This is such a pleasure. Yeah, as Bahadur said, my name is Wahid. I'm a PhD student at Purdue University, and I work on consistent modeling of materials. This talk is going to be on generative hyperelasticity with physics-informed probabilistic diffusion fields. And this is a work that's currently under review in engineering with mechanics. So there are two keywords in this title, hyperelasticity and diffusion. And indeed, this talk is actually two talks hidden in one, because the work that I introduced here is actually built on another piece of work that we did a couple of years ago on hyperelasticity. And so I'll start with introducing that part of the work, how we do data-driven physics-informed hyperelasticity, and then I go into the diffusion part of the work. So let's start with hyperelasticity. Hyperelasticity is defined using an equation, which is given here. P equals d psi df, where P is the first Pilo-Kirchhoff stress, psi is the so-called strain energy density function, or SEDF, and F is the deformation gradient. We can alternatively write this using S and C, other forms of stress and deformation. And when you're using invariant-based hyperelasticity, the strain energy density function, or SEDF, becomes a function of invariance I1, I2, I3, etc. And S takes this form that I show at the end. Now, the derivatives of the invariance with respect to the deformation tensor C is just pure algebra. But this other part of the equation, which are partial derivatives of the SEDF with respect to the invariance, is actually material specific. And the lesson that I want you to take home from this slide is that in hyperelasticity, there exists this function known as the SEDF, which completely defines the material. So if you know the SEDF, you know everything there is to know about the material, or alternatively, if you know these partial derivatives. And so it's no wonder that over the years, many research groups around the world have been trying to come up with different forms of the SEDF that can explain different material behavior well. And this is an ongoing list. Every year we see many new models coming up. But we ask a different question. Why not let the machine find out what the SEDF should be? Right? Because machine learning models like neural networks are famously known as universal approximators, so let them do the work. And that's exactly what we did, but you can't just plug in the invariance into a neural network and call it a day, because you need to satisfy some physics-based criteria, such as objectivity, material symmetry, thermodynamic consistency, etc., and perhaps most importantly, polyconvexity. Now, polyconvexity is a very nice criterion. It guarantees the existence of global minimizers, but at the same time, it allows for multiple minima when needed. It assures that the material is physically realistic, etc., etc. And mathematically, it's defined as such. An SCDF is polyconvex if it's a convex function of the deformation gradient f, cofactors of f, and determinant of f. Or when we're using invariant form and we're interested in the stress, these partial derivatives from the previous slide that you remember, these are supposed to be monotonic and non-negative. And so now we're faced with this dilemma. Somehow we need to model these functions using data-driven functions so that they are flexible and expressive, but at the same time, we want to limit them to the space of functions that are only monotonic and that are only non-negative. How can we do this? Well, we solved this problem using so known as neural ordinary differential equations, or NODEs. Now, an NODE is a computational framework similar to a neural network, except it's defined as the output of an ordinary differential equation whose right-hand side is a neural network. The inputs of the NODE constitute the initial conditions of this ODE, and the solutions of this ODE at some predetermined time are the output. So for any value of the input, you integrate that ODE up to the final time, and that is your output. And be aware that at every step of the integration, the right-hand side is a neural network evaluated at that time. But here's the thing about ODEs. Their solution trajectories never intersect, which means that the input-output map of the neural ODE is always monotonic. And I'm going to come back to the details of this in the tutorial if we have time. But for now, we use this NODE concept in this paper to generate hyperelastic material models that are always polyconvex, that satisfy all the physics-based criteria, and at the same time, they can capture different kinds of material behavior really well. And we used it in a finite element package to do this virtual surgery on the scalp of a cancer patient, actually. But monotonicity and convexity are such ubiquitous phenomena in physics that they show up everywhere. And we've used the same NODE concept for hyperelasticity, for viscoelasticity, for damage, and others. And if you're interested, you can go to these references to see for yourself. But that was the hyperelasticity part. Now, going into diffusion, let's start by defining diffusion. Diffusion is a score-based generative model. So what's a generative model and what does score-based mean? Well, let's start with the generative model. A generative model is a model that is tasked with sampling more samples from a distribution given some existing samples. I know that sounds a little convoluted, but bear with me. So suppose you have some data that in this case is in the form of some dog images. The assumption here is that these come from some underlying distribution, and we want to model that distribution. Because if we have the model, we can sample more images or more data from that model. Now, to approach this problem, maybe a naive approach would be to just feed the data into a feed-forward neural network to obtain the probability distribution, a probability density function. But this doesn't work. Instead, we can take the output of the neural network and exponentiate it so that it's always positive. And then we need to divide it by the normalizing factor z theta, such that p at the end is always between 0 and 1. But this z theta, or the normalizing factor, is an extremely difficult quantity to find because it involves integrating over the entire input space, which in this case would mean integrating over all the possible dog images. And so instead, we prefer to work with score functions rather than probability density functions. So a score function is just the derivative of the logarithm of the density function. And here I'm showing the density function in color and the score function using the arrows to show you that they are equivalent. But the good thing about the score function is if you take that neural network form of P and you plug it into this equation, you see that Z is constant and it goes away when you differentiate it. And you're only left with this part, which is just the derivative of the output of the neural network, which is a very easy thing to take. And so with this in mind, we use generative models in hyperelasticity. They have a bunch of more really outstanding qualities, especially when compared to other generative models, but I won't go through all of them right here to save time. I'll just go into some uses of diffusion. Diffusion is becoming really famous nowadays. It's used in text generation. It's used in image generation, like in DALL-E, and also even video generation, aside from all the scientific uses. We have image and video here, but nowadays I think Sora is a much more outstanding example. And to briefly touch upon how diffusion works using two stochastic differential equations, or SDEs. The forward SDE takes some input data and gradually corrupts it until it becomes pure white noise. But in this process, we end up learning the score function of this data. And then once we have that, we can use the reverse SDE to go from white noise to meaningful data. And that's the essence of how diffusion works. Now, we use diffusion not with images, not with videos, but with physics-informed NODE-based models of hyperelasticity in this paper that I cite here. So a brief overview of how this model works is, I think, best explained through this diagram. We have some stress-stretch data from a family of materials. Let's say the skin of a number of mice. We use that data to train our NODE-based models of hyperelasticity. And then the weights and biases of those NODEs become the training data of our diffusion model, in which case the forward SDE just turns them into garbage. And then once we have the trained diffusion model, we can start from white noise and generate new samples of NODEs pertaining to this family of materials. We can then use those NODEs to make stress strain predictions, and this allows us to quantify the uncertainties and the distributions in this family of materials. Here I show an example of this in using synthetic data. So I generate some synthetic stress stretch data using a May-Newman type strain energy density function. And on top right, you see the orange curves, which are just different members of this family of materials, stress versus stretch. And then at the bottom row in panel B, I'm showing that as you increase the number of samples from this family used for the training of the diffusion model, the model captures the distribution of the data more and more accurately. Here I'm showing the parameters that the diffusion model captures. So the orange curves here are the distribution of the data, and the gray curves are the model. And as you can see, the diffusion model does a very good job of capturing even the bimodal distributions in these parameters. And then we work with some experimental data. Now, in the actual paper, you'll see that I'm showing examples for murine skin. Here, I wanted to have a change of pace, and I'm showing another example where we use opacified sheets, which are used as insulation material in hypersonic vehicles. And I have data for around 15 different material samples. As you can see, they are quite different from each other. There is a significant variation in material properties from one sample to another. But overall, you can see that they are still the same family of materials. And it's worth investigating how their stress response changes. And so we use this data to train the diffusion model and before that, we trained the NODEs with every single one of these. And as you can see, the NODEs capture that individual stress-strain response really, really well. And then we use these NODEs to train the diffusion model and make predictions with some new samples from that family. Here, the orange curves, orange dots, are the data that I showed you before, and the gray curves are newly generated samples using the diffusion model, which shows you how it captures that behavior of the family, as well as the distributions, the standard deviation from the mean, etc., etc. One cool thing about diffusion is that there are a lot of cool things about diffusion, but one of the things is that we can use simple Bayes rule to do conditional diffusion. So suppose you have this density function or the score function for the opacified sheets. Now you want to condition that the outputs of the diffusion model on some observations. So P of X given some set of observations. You can simply apply Bayes rule here, and the updated score function, the conditional score function, is obtained as such, where this last term goes away. This second to last term is the score function that we already learned, and this conditional score function is just a classifier that we train. So here, I'm doing exactly that. I have trained my diffusion model on the data that I showed you. And in top row, I'm showing all of that. Plus, I'm showing observations for a new material in orange. And when I condition the diffusion outputs on those sets of observations, the green lines is what I observe. So I can learn from a family of materials and apply it to an individual material at the end. At the bottom row, you see the distribution of the parameters of the NODEs before and after conditioning. And one last thing that I want to touch upon is using Gaussian fields. Using spatiotemporal Gaussian fields, we can also generate spatially correlated diffusion fields, which means we can generate heterogeneous materials for a given family of materials. Here I'm showing those fields for a number of length scales. And we use these in a finite element package to study the characteristics of heterogeneous materials. And that's basically it. So to sum up, there are two parts. Hyperelasticity, we use NODEs to satisfy a number of physical criteria, as well as giving the model a lot of flexibility. And then we use this hyperelastic model inside the diffusion model to study the characteristics of a family of materials rather than a single material, and study heterogeneous materials. I think that was it. Yeah, thank you for your attention. I hope I didn't run over time. And if you have any questions, please let me know.
Thank you. It was really on time and great talk. Do you have, so we have, there is an option that like, if you have some sort of code to illustrate something in a Jupyter or something like that, we have like 10 minutes for that. Do you have something like that?
I've prepared the tutorial.
Okay, that's great.
Yeah.
So if anyone has question for this part, they can just raise hand or just unmute and ask the question or put it in the chat. Still, after this, we're gonna have also Q&A. They can also ask it. Probably you can just start like bringing up the code, and if someone asks, yeah.
Okay, so here are step-by-step instructions for opening up the tutorial. I've created this GitHub repo for this tutorial. You can just copy this and paste it into Google Colab if you want to follow online. So I'll leave this up for 1 or 2 minutes if anyone wants to follow online. Okay. So after pasting it, make sure to click on the search icon, and then this notebook should hopefully show up. If you click on the notebook, you'll open up this notebook that's aimed to demonstrate some qualities of the NODEs that I discussed. I thought diffusion would be too complex for a short tutorial, so I opted to do one based on NODEs. So what I'm doing here is just importing the necessary packages, which are mostly JAX. I work with JAX, but you can use TensorFlow or PyTorch for this. And I'm also importing matplotlib.pyplot for plotting. So I run that first cell. And now here, as a baseline, I have just a simple run-of-the-mill feed-forward neural network. This is nothing out of the ordinary, just the ordinary feed-forward neural networks that you see everywhere. And then I have this helper function to sample the weights and biases, to initialize the weights and biases of the neural network. But you can do that manually too if you want. So now that I have these two functions, what I do here is this is just used for generating a random number generator key. And then I initialize the parameters of my feed-forward neural network using this function. Then I call the FFNN, or feed-forward neural network function, for some values of the input. So in this case, my input varies from 0 to 1, and I call that function with randomly initialized weights and biases. When you do this, you should see some input-output pair like this. But this is a feed-forward neural network, and the output is arbitrary. It can be anything. It can be increasing, it can be decreasing, it can be monotonic, it can be non-monotonic. There's no guarantee. Every time you run this cell, you will see a different kind of behavior. But then here I have a NODE, which just calls that FFNN function at every time step, and then integrates the function from time 0 to time 1. And now I'm going to do the same thing with a NODE. So just sampling parameters with a new RNG key, and then getting the outputs for a given set of inputs. Here is what the output of the NODE looks like. Now I'm going to do the same procedure 100 times over, and you might have noticed that there is something strange going on here. These are all monotonically increasing curves. None of these is non-monotonic. And that basically aims to demonstrate how NODEs work. We can go a little further. We can even force the NODE to start from the origin, to map 0 to 0, and then to be a monotonically increasing function. To do that, I just remove the biases of the feed-forward neural network. If you remove the biases, everything is a series of multiplications, and an input of 0 is mapped to an output of 0. So now this is a slightly modified version of that FFNN function that I show above. And this is a slightly modified version of NODE that uses this function rather than FFNN. And when I use this, as you can see in the image, all the curves now start from 0. So they map 0 to 0, and then they are monotonically increasing functions. Which, again, as I said, is a very useful criterion in physics, right? Monotonicity, convexity, and then controlling the values at certain points are all highly useful characteristics when modeling physical phenomena. In fact, as I said, we've used this in a number of cases, like even recently damage modeling. Before that, we had anisotropic finite viscoelasticity. And then before that, hyperelasticity, you're all relying on this simple but highly useful characteristic. But yeah, that's the end of the tutorial. Please let me know if you have any questions, or you can email me anytime if anything comes up. I'm happy to help.
Is there any question from the audience? Probably if there is no question, then I can ask something, then maybe probably other people also can ask. Going back to the diffusion, using diffusion denoising for hyperelasticity, my question is, what would be the use case of like doing that?
Right. So the hyperelastic model is for studying the characteristics of one material, and the diffusion model is for studying the characteristics of a family of materials. So in a lot of cases, you're interested in studying how the hyperelastic properties of a material changes in a family of materials, so that you have an idea of the uncertainties that you can expect when using this family of materials. You can also use diffusion models as a sort of transfer learning method. So say you have a lot of data from the population, but you have limited data from one individual. You can learn the score function for the entire family and then narrow it down to this specific individual so that you have you retain that knowledge from the family as well as maximizing your set of observations, right?
But like if I'm concerned like about a family of responses in the feed-forward sense, I can do that through the lens of Bayesian learning, the Bayesian neural network. Like I can put a distribution on my parameters, and then now I can learn like a distribution of families, right?
Right. So that's indeed true. And one thing I want to point out is diffusion is a Bayesian method. So this is still, again, looking at the same problem through the Bayesian lens, but through a different tool set. And the reason that we don't opt out for Bayesian neural networks or similar probability distribution estimation functions that were devised before is that diffusion is really, really powerful. I'm going to say, so if you go back to, actually, I can't show it now, but in one of my slides, I showed the synthetic data case, and we try to capture that distribution using a different probability estimation tool, which in this case is a mixture of Gaussians. And it simply doesn't work when you have, it works if you have a small data set, if you're working with a small dimensionality of the problem. But when you're using data-driven models with hundreds of parameters, conventional tools like Bayesian neural networks or mixture of Gaussians becomes really, really difficult to use unless you have a ton of data. Unlike
that sort of makes sense for difficult tasks, but if you bring up your slide on the actual hyperelastic problems, the variation in the response is not that high. So which means like you don't have, in the reality of the hyperelastic material, you don't have that much complexity similar to like images, right?
Right.
If you go to the like the real data from the experiment you show.
Right. The
Yeah, that one.
dimensionality. Yeah.
Yeah, clear. So these are honestly, to me, maybe I'm wrong. These are just one family with different parameters. So if you care with one of these things with one of the right classical hyperelastic material, and then playing around the parameters, you can capture all of them.
Right. The thing is, these do not represent the dimensionality of the problem. The dimensionality of the diffusion problem lies in the size of the neural networks that you use in your neural ODE. Now, the point is, in this case, they look simple, but the material behavior can be extremely complicated. And to capture that, you need neural networks that have, say, 500 parameters. Every neural ODE has 500 parameters.
Do we, in reality, do we have like do you expect some material have like sinusoidal response?
Not sinusoidal, but yes, we do have that example.
I think to me, based on I want to see like have you seen such a thing? to me, most of these hyperelastic materials in this setup, they are more or less similar to this, right? They have this kind of, we just did some degree of variation.
Yeah.
But compared to the image case, in the image case, the space of the space that image is generated is really complex. This is my intuition. Maybe I'm wrong.
That's definitely true. An image has, say, millions of pixels, each of which has 3 RGB values plus an alpha value. So 4 times, say, 10 million. That's a lot more than this case. But the comparison here should be more between data-driven hyperelastic models and traditional hyperelastic models. So traditional models have a handful of material models, material parameters. Data-driven models have hundreds. Now, conventional UQ methods like Bayesian neural networks or mixture of Gaussians work really well, in fact, with say, up to 100 parameters, but not very well beyond that, unless you have millions upon millions of data points. You see what I mean? So in this case, for example, this may look simple to our eyes, but to exactly capture this behavior may necessitate using hundreds of parameters. And when you have neural ODEs of that size, estimating the distribution in this family requires a powerful tool, in this case, we use diffusion for that. Of course, diffusion is not the only model.
This is true, and that's why in one of my work I tried to converge like the neural network to like analytical representation. Basically, when you have that kind of analytical representation with like at most 5-6 parameters, then you can just put like any probability distribution on those parameters and just try to like do the posterior estimation, right?
Right. Yeah. If you're working with an analytical function, it becomes much more easier. Exactly.
I see. Interesting. And like how long it takes to train these models, and how large are those models, and how many like trajectories or samples do you have to train those models? Like, I mean, diffusion model for this problem.
Right. So training doesn't take a lot of time. Training the NODEs like this is usually less than a minute, I would say, if for each one of these. And then training the diffusion model itself is, again, not that costly. It's probably less than 15 minutes. But going into the number of curves that you need for training, we haven't really tested the limits of the diffusion model on this. That would require a very thorough study of how you overestimate, or what's it called? Overfit the data, at what point you need more data, etc., etc. But so far, we've been using from 10 to 50 materials from a family, and that's been working really, really well. We haven't seen any issues of either overfitting or underfitting, basically.
Good.
Quick question. So for each material, when you try to train the neural ODE for that, do you take multiple training samples, like try to train it multiple times, because the parameters are not always going to be unique, right?
Right. I think we mostly use no batching. So the entire data set for that family, for that material, is used at once. And simply because we have no issues of overfitting, basically. So we're not worried about overfitting. We're not worried about noise that much. So we use all of the data at once.
I see. Thanks.
No problem.
Any other question from audience? If there is no question, then we can call it a day and thank our speaker.
Yeah,
no
thank you for the
question.
presentation. Yeah.
Thank you, Wade. Very nice presentation. Interesting research. Thank you for taking the time.